The quest for life beyond Earth leads us away from our familiar world and into the deep reaches of the cosmos, where alien landscapes wait to be explored. Among the countless planets orbiting distant stars, a few stand out as possessing the conditions necessary to sustain life, perhaps in forms we have never even imagined. As we look ahead, we ask which of these worlds are most likely to harbor life, holding the answers to humanity's oldest questions hidden on their distant horizons. It is a long story, one we might first explore in our dreams, but before we dive in, remember to like, follow, and share this journey. In 1992, astronomers Alexander Wolfson and Dale Frail discovered two planets orbiting a pulsar, a rapidly rotating neutron star known as PSRB 1257+12. These pulsar planets were born from the chaotic debris of a supernova, an incredibly harsh environment, yet their discovery proved that planets could exist in places once thought impossible. Interestingly, these worlds did not orbit a sun-like star, defying the expectations of many theorists and forcing scientists to rethink the environments where planets can form. Since then, the hunt for exoplanets has accelerated, with astronomers refining their techniques to scan more consistent regions of the Milky Way. If you pointed a telescope at the night sky, what are the odds of finding an Earth-like planet? Surprisingly, the chances are small but hopeful. Estimates suggest only about 1 in every 10,000 stars might host an Earth-like world. However, in a galaxy with hundreds of billions of stars, this still translates to millions of potential candidates. The discovery of super-Earths and mini-Neptunes has further expanded the variety of planetary blueprints, showing us that our solar system is just one of many possibilities. Finding an exoplanet is like trying to spot a moth fluttering next to a distant streetlight. It is a massive challenge, but astronomers have developed ingenious methods. The transit method, for instance, detects planets by measuring the slight dip in a star's brightness as a planet passes in front of it. This technique has helped us find many small planets within habitable zones. Another method, radial velocity, measures the tiny wobble of a star caused by a planet's gravity, allowing us to find worlds that the transit method might miss. This has been particularly effective at finding hot Jupiter's massive gas giants orbiting extremely close to their stars. These discoveries challenged early assumptions about planetary formation, leading to new models that explain how these giants migrate inward from the outer reaches of their systems. A less common but fascinating method is astrometry, which tracks the precise motion of a star over time to detect gravitational influences. While not yet widely used, it holds great promise for finding Earth-like planets in the future. Hot Jupiters are massive gas giants with scorching surface temperatures due to their proximity to their host stars. Their existence upended traditional theories, as scientists once believed gas giants like Jupiter could only form in the cold outer regions of a system. However, planets like 51 Pegasi b were found orbiting closer to their stars than Mercury is to our Sun. These worlds possess bloated atmospheres and searing surfaces, forcing a total reconsideration of planetary migration and orbital dynamics. Planets are born within protoplanetary disks swirling rings of gas and dust around young stars. These glowing disks emit infrared and radio radiation, allowing astronomers to study the earliest stages of formation as dust grains collide to form planetesimals, the building blocks of worlds. By observing these disks, we better understand the origins of all planetary systems, including our own. The search for life often begins with the study of exoplanet atmospheres. When a planet transits, a fraction of the starlight passes through its atmosphere, allowing us to analyze its chemical composition. This has revealed water vapor, methane, and even carbon dioxide. However, hazes and clouds can complicate these readings, masking or altering the signals. For example, absorption lines of sodium and potassium indicate hot gaseous environments, while molecules like methane might hint at biological activity. Detecting these faint signals is a testament to the precision of modern astronomy. Many exoplanets orbit so close to their stars that they are tidally locked. One side faces the star in eternal day, while the other remains in perpetual darkness. While this seems inhospitable, the twilight zone along the border between day and night might offer moderate conditions suitable for life. These environments demonstrate the diverse habitable conditions that may exist beyond Earth. Some exoplanets even have retrograde orbits, traveling in the opposite direction of their star's rotation. This phenomenon challenges existing models, suggesting that such orbits result from intense gravitational interactions or violent early collisions. Furthermore, many exoplanets exist in binary star systems, where two stars orbit each other. Planets in these systems face complex gravitational forces and unpredictable orbital dynamics, yet they might also experience long, stable days under the light of two suns, creating unique habitable environments. Unlike the planets in our solar system named after mythology, exoplanets are typically given alphanumeric designations for scientific clarity, such as Kepler 452b or TOI 700d. While practical, these names lack the romanticism of Mars or Venus. However, initiatives like the International Astronomical Union's Name Exo-Worlds campaign have given the public a chance to name these distant places, adding a human touch to the stars. The characteristics of a host star play a vital role in habitability. Stellar flares and radiation can strip an atmosphere or bathe the surface in ultraviolet light, making magnetic fields and long-term stellar stability crucial for life. The interaction between a planet and its star is a delicate balance that shapes the evolution of the planetary environment. The discovery of exoplanets has revealed a universe far stranger and more diverse than we imagined, from scorching hot Jupiters and wandering rogue planets to Earth-like candidates and ocean worlds. Each discovery brings us closer to answering if we are alone. What makes a planet habitable? This is the core question. We aren't just looking for any planet, but specific environments where life can thrive. Earth is our only reference, but habitability is about more than just finding liquid water. The vast universe may hide surprises beyond our current understanding. Next, we explore the subtle, often overlooked factors of habitability, such as the complex links between planetary and stellar traits that must work together to support life as we know it or life in forms we have yet to conceive. Liquid water is the gold standard for habitability, but the conditions required to keep it liquid are complex. High atmospheric pressure can allow water to remain liquid at extreme temperatures, broadening the range of potential habitats. Tidal heating from nearby moons or stars can also generate internal heat, melting subsurface ice into liquid oceans, much like Europa or Enceladus in our own system. Conversely, slowly rotating planets might see water trapped in frozen poles, limiting its distribution. However, life might not always depend on water. Alternative solvents like methane or ammonia expand the possibilities of alien biochemistry. While tidal locking was once seen as a barrier to life, new models suggest that atmospheric circulation can distribute heat across a planet, creating stable regions even on the dark side, provided geothermal energy prevents total freezing. The metallicity of a star, the abundance of elements heavier than hydrogen and helium, also influences planet formation. Stars with high metallicity are more likely to form rocky planets, the foundations of Earth-like worlds. Interestingly, the distribution of metallicity in the Milky Way suggests the inner regions may be richer in rocky planets, while low metallicity stars, though rare, have fewer gas giants to gravitationally disrupt smaller worlds. A planet's magnetic field is its primary defense against stellar radiation. Without it, stellar winds could strip away the atmosphere, as happened with Mars. Magnetic fields are generated by the movement of molten metallic cores, and larger planets may maintain these fields longer as their cores cool more slowly. Habitability isn't just about having an atmosphere, it's about protecting it from relentless cosmic forces. On Earth, the carbon silicate cycle regulates global temperatures over geological time scales. Similar cycles on exoplanets could stabilize climates, where volcanic activity releases carbon dioxide to warm the planet, and weathering removes it to cool it down. Without such feedback, planets risk runaway effects, becoming frozen like Mars or overheated like Venus. Plate tectonics are a key feature of this geochemical cycling and thus a vital factor in habitability, even if they are difficult to detect directly. Planetary size also matters. A planet that is too small, like Mars, may lose its atmosphere over time, while one that is too large, like Neptune, may retain a thick envelope of hydrogen and helium that is inhospitable to life. Super-Earths, planets larger than Earth but smaller than Neptune, are of great interest because their stronger gravity can maintain thick atmospheres and active geology for billions of years. We often view oceans as symbols of life, but their geological role is equally critical, as they transport heat from the equator to the poles and regulate atmospheric composition by absorbing gases. Subsurface oceans beneath ice layers could also support life in harsh conditions. A planet's albedo, or the proportion of light it reflects, also dictates climate. High albedo from ice or clouds can lead to global freezing, while low albedo can cause a runaway greenhouse effect. Finally, the concept of the abiogenesis zone expands our view beyond just liquid water to include energy gradients and complex chemistry essential for the origin of life. The lifespan of a star also dictates the window for life. Massive stars live only millions of years too short for complex evolution, while red dwarfs can last trillions of years. Our search for life is not just a journey across space, but an exploration into the nature of existence itself. While we imagine distant galaxies, some of the most promising candidates are within a few dozen light years. Proxima Centauri b, just 4.2 light years away, is a rocky world in its star's habitable zone. Though it faces intense stellar flares, its proximity makes it a primary target for future interstellar missions. Another candidate, LHS 1140b, orbits a quiet red dwarf 40 light-years away. With its dense rocky core and stable environment, it is considered one of the best cases for a habitable super-Earth and a key focus for the James Webb Space Telescope. In 2017, astronomers announced the groundbreaking discovery of a system featuring 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1, located just 39 light-years away. Within this system, 3 planets TRAPPIST-1e, F, and G reside within the habitable zone. TRAPPIST-1e is remarkably similar to Earth, with density and composition suggesting a rocky surface. TRAPPIST-1f is believed to be a potential water world, possibly covered by a global ocean, while TRAPPIST-1g is larger and colder but may harbor a subsurface ocean of its own. Although these planets are tidally locked, they are spaced so closely together that they present a fascinating hypothesis for life. Should advanced civilizations exist there, traveling between planets could be as routine as crossing continents on Earth. Another compelling candidate is Ross 128b, orbiting a quiet red dwarf only 11 light-years away. Unlike Proxima Centauri, its host star is far less active, providing a significant advantage for habitability. Ross 128b receives radiation levels similar to Earth, suggesting temperate surface conditions. With an orbital period of 9.9 days, it sits firmly within the habitable zone, and the low stellar activity increases the likelihood that it has retained its atmosphere, making it a primary target for studying life around red dwarfs. Further afield at 12 light-years, GJ 1061d orbits a red dwarf at the outer edge of its habitable zone. With a mass approximately 1.75 times that of Earth, it is likely a rocky world where temperatures could allow for liquid water under the right conditions. Though less studied, its proximity makes it a vital subject for future observations. Similarly, Barnard's star B is a super-Earth located only 6 light-years away, orbiting the second closest stellar system to our own. While it orbits in a frigid region beyond the traditional habitable zone, geothermal activity could potentially maintain liquid water beneath its surface. As one of the oldest stars known, Barnard's star offers a window into early planetary systems and challenges our assumptions about where life can survive. Meanwhile, Tau CDF orbits a Sun-like star 12 light-years away. Situated at the outer boundary of the habitable zone, it would require a thick atmosphere to prevent its surface from freezing. The low metallicity of this system provides a unique perspective on how planets form in environments with fewer heavy elements. In 2019, Teegarden's star C was discovered orbiting an ancient star 12 light-years away. This system contains 2 planets near the habitable zone, with Teegarden's star C scoring high on the Earth Similarity Index, offering a stable environment that has existed for billions of years. Another super-Earth, Wolf 1061c, lies 14 light-years away at the inner edge of its habitable zone. Despite extreme temperature variations due to its proximity to the star, atmospheric circulation might create habitable niches. Perhaps most intriguing is Captain B, located 13 light-years away. This super-Earth is over 11 times the mass of Earth and orbits one of the oldest known stars. At over 11 billion years old, twice the age of Earth, this world has had more than enough time for life to emerge, evolve, or even vanish, allowing us to study how habitability evolves over vast cosmic time scales. These nearby worlds are the focus of the James Webb Space Telescope and the upcoming extremely large telescopes, serving as beacons of hope that other homes exist among the stars. The atmosphere of a planet is not merely a shroud of gas, it is the key to understanding its climate and biological potential. By analyzing the spectral fingerprints left as starlight passes through these atmospheres, scientists can identify specific molecules. This technique has revealed water vapor, carbon dioxide, and methane on distant worlds. For example, the hot Jupiter WASP-39b, 700 light-years away, showed high concentrations of sulfur dioxide driven by photochemical reactions, alongside water vapor and sodium. Some planets, like the Neptune-like GJ 3470b, possess helium-rich atmospheres that are slowly bleeding into space, forming giant glowing tails under ultraviolet light. These discoveries highlight how intense stellar radiation reshapes planetary envelopes over time. Weather on exoplanets often defies human imagination. On HD 189733b, a hot Jupiter 64 light-years away, winds howl at over 10,000 km per hour faster than the star's own rotation. The atmosphere likely produces glass rain made of silicate particles that are whipped sideways by lethal storms. Other worlds, like GJ 1214b, are shrouded in thick hydrocarbon or sulfur hazes that mask the surface, creating colorful yet opaque skies. Some planets even exhibit temperature inversions, where the air gets hotter with altitude due to the absorption of radiation by molecules like titanium oxide. While water vapor has been found on planets like the super-Earth K2-18b, nitrogen, the primary component of Earth's air, remains elusive in data, possibly due to its weak spectral signature. Finding a nitrogen-rich atmosphere would be a landmark discovery, signaling Earth-like conditions. Furthermore, observing the coexistence of oxygen and methane would be the holy grail of astrobiology, as these gases react and disappear unless constantly replenished by living organisms. While we often focus on planets, moons play a critical role in habitability. In our own system, the moon stabilizes Earth's axial tilt, preventing wild climate swings. Large exomoons could perform the same function for distant planets, ensuring predictable seasons. Moons can also be heated by tidal forces, keeping subsurface oceans liquid even far from a star, as seen with Europa and Enceladus. These moons might even act as shields, deflecting cosmic debris away from their host planets. If a moon possesses a metallic core, it could generate its own magnetic field, adding an extra layer of protection. Some moons might even have their own atmospheres fueled by volcanic activity, maintaining temperate climates through the greenhouse effect. Even rogue moons, ejected from their home systems to drift through the interstellar void, could potentially carry the remnants of life within protected, ice-covered oceans. The search for life is expanding beyond the horizon of planets to include these diverse and dynamic satellites, reminding us that the universe is far more hospitable than we once dared to dream. Most exomoons are expected to be tidally locked to their parent planets, meaning one side always faces the planet while the other faces away. This state creates unique environmental conditions. The side facing the planet may have its temperature moderated by reflected light and heat, while the far side remains much colder. This temperature gradient between hemispheres could drive atmospheric circulation, distributing heat to more distant regions. While tidal locking presents challenges, it also creates niche opportunities for habitability. Detecting these moons remains a monumental task due to their small size and faint signals. One potential method is transit timing variation, where a moon causes a slight advance or delay in its planet's transit across a star. While direct imaging is currently impossible, next-generation telescopes may eventually bridge this gap. Despite the difficulties, the indirect detection of exomoons will remain a vital frontier in future research. Planets are not static entities, they evolve over billions of years, shaped by their formation processes, internal dynamics, and cosmic events. Exoplanets are no exception, undergoing continuous transformations that determine whether they become scorched hellscapes, frozen wastes, or cradles for life. One of the most surprising discoveries is the tendency for planets to migrate. Unlike the orderly arrangement of our solar system, many exoplanets move significantly from their birthplaces. Hot Jupiters are a prime example. They likely formed in the cold outer reaches of a system before migrating inward due to interactions with the protoplanetary disk or neighboring planets. Such migrations can destabilize a system, ejecting asteroids or altering orbits, sometimes even resulting in highly eccentric outward paths. This reveals the chaotic and dynamic nature of planetary systems. An atmosphere acts as both a shield and a vulnerability. Over time, stellar radiation and cosmic events can strip an atmosphere away. Planets orbiting close to active stars, such as those around red dwarfs, are particularly susceptible to losing their air to stellar winds and flares. Smaller planets with weak gravity, such as Mars-like worlds, struggle to retain their gases and eventually dry out. Typically, lighter elements like hydrogen and helium escape first, leaving behind secondary atmospheres formed by volcanic eruptions or impacts. The gain or loss of an atmosphere often dictates a planet's potential for life, highlighting the fragile balance of habitable environments. Collisions between planets play a pivotal role in their development. Earth's moon is believed to have originated from a giant impact between the young Earth and a Mars-sized body. Such collisions can strip away atmospheres, reset surface compositions, and alter rotational states. For instance, the extreme axial tilt of Uranus may be the result of a massive impact. In exoplanetary systems, these violent encounters can trigger volcanic activity and introduce water or organic compounds, providing a new starting point for planetary evolution. Runaway greenhouse effects serve as a reminder that evolution can lead to catastrophe. Venus is the classic example, where a thick carbon dioxide atmosphere traps heat so effectively that the surface can melt lead. A similar fate could await Earth-like exoplanets if they lose their water or accumulate excessive greenhouse gases. This underscores the thin line between a habitable world and an uninhabitable one. The evolution of a planet is inextricably linked to the activity of its host star. Young stars are often violent, emitting intense ultraviolet and X-ray radiation that can alter surface chemistry and strip atmospheres. As a star enters its stable phase, much like our Sun, it provides billions of years of consistent energy, allowing complex ecosystems to develop. Conversely, the death of a star can devastate its system. Planets orbiting white dwarfs are exposed to intense radiation and shifting gravitational forces. Understanding stellar activity is therefore essential to predicting a planet's long-term fate. Furthermore, the metallicity of a star, the ratio of elements heavier than hydrogen and helium, greatly impacts planetary formation. High metallicity stars are more likely to harbor rocky worlds, as these heavy elements are the building blocks of planetary cores. Low metallicity systems tend to produce more gas giants or icy bodies, with fewer Earth-like planets, which paradoxically reduces gravitational disruptions. Stellar chemistry provides a window into the diverse evolutionary paths of systems across the galaxy. In the coming decades, humanity will possess unprecedented tools to explore these worlds. The James Webb Space Telescope has already begun revealing the atmospheric secrets of distant planets, and next-generation facilities like the Extremely Large Telescope and the Habitable Worlds Observatory will follow. These instruments will allow us to study the chemical signatures and potential biosignatures of smaller, colder, and more distant Earth-like planets. Direct imaging technology will be the key breakthrough. Using advanced starshades and adaptive optics, we hope to clearly see the outlines of distant exoplanets for the first time. Such observations will help us determine surface features, cloud patterns, and the presence of oceans. Methods like gravitational microlensing, transit timing, and radial velocity will continue to work in tandem to refine our understanding. As our precision improves, we will be able to analyze trace gases for any signs of life. The exploration of exoplanets is our response to the great unknown, a journey where every distant world acts as a mirror reflecting our own questions about life, home, and the future. Behind every faint point of light in the night sky, there may be another world waiting to be found. That concludes our journey for today. I hope this brings you sweet dreams, and I will see you in the next episode.